Okay, we're going to do some more sample problems for Chem 111. Today we're doing problems doing significant figures and then continuing some dimensional analysis taking into account those significant figures. So first, let's look at this problem. Let's express the result of this calculation with the correct number of significant digits. So we're going to take 13.602 times 1.90 times 3.06. Take all of that divided by 4.2 times 1.4097 to get our solution. So we must remember that when we're talking about multiplication and division, when we multiply or divide, the rules for this is that we're looking at the answer, the solution, the number of significant digits in the answer is going to be the one with the least number of significant digits from the initial numbers. So if we go back up here, we have to figure out how many numbers of significant digits are present in each one of these numbers, and then since we're multiplying and dividing, the smallest number is going to give us the number of digits, significant digit we should have in our answer. So if we look here in the 13.602, all of these numbers are significant, so that has a total of 5. Here, 1.90, this one is significant because it's after the decimal, to the right of the decimal, and preceded by a non-significant or another significant digit, non-zero digit. So this has 3. Again, 3.06. Again, this 0 here is between two non-zero numbers, so it is significant, so it also has 3. Here we have 2 non-zero numbers, so there are 2 significant digits here. And again here, because this 0, like the rest of them, are in between non-zero numbers, this has 5. So the smallest, the least number of significant figures is 2. So that means our answer should be displayed with 2 significant figures. So we follow the order of operations. We multiply this across, multiply this, divide those 2 numbers together. We get, from my calculator, 13.35678. But because we can only have 2 significant figures, we need to round this to 2 significant figures. So this becomes approximately 13. Right? Again, 2 significant figures, 2 significant figures. Let's look at another one. Here we're going to express this one in the number of significant figures. 13.914 centimeters plus 243.1 centimeter plus 12.00460 centimeters. Notice in this case we are adding or subtracting. So when we're adding or subtracting, now we have a different set of rules for significant figures, and we're going to go the solution has the smallest number of decimal places. Right? So we're going to look here. We're not really worried about how many total significant figures there are in these numbers. We're just looking for the smallest number of decimal places. So here we have 3 decimal places. Here we have 1 decimal place, and here we have 5 decimal places. So because this is 1 decimal place, our answer is going to be reported with only 1 decimal place. So again, if we do this addition, add these all together, we get 269.0186 centimeters. But because of the rules of scientific notation, we have to round that to 1 decimal place. So this becomes 269.0 centimeters as our final solution. So let's start using these significant figures in some of the conversions we've talked about before. So we have isopropyl alcohol, commonly known as rubbing alcohol, boils at 82.4 degrees Celsius. What is the boiling point of this in Kelvin? So if we remember, to go from Celsius to Kelvin, the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So if we want the temperature in Kelvin, we're going to take our temperature in Celsius and add 273.15. So when we do that, we get an answer that is 355.55 K. Again, remember when we're talking about Kelvin, it's an absolute scale, so there is no degree symbol. We just use the capital K. Right? But we also have to take into account the number of significant digits. Here, since we're adding and subtracting, we're going to use the smallest number of decimal places, so that it's going to be 1. So we have to round this number to 1 sig fig, so this becomes 355.6 Kelvin. Again, do the actual math first, and then at the end, go back and worry about significant figures. Let's look at a couple of examples where we're using dimensional analysis. Right, so if the price of gold at the morning fixing in London was $5,310 per pound, what would a kilogram of gold cost in British pounds? The symbol here is for pounds, assuming the exchange rate between the dollar and the pound was $1 equals 0.545 pounds. Right? So the trickiest thing about here is going to be converting between and keeping the pound as the dollar amount or the currency amount consistent with the pound, the mass amount or weight. So we're going to start with what we have here. We have this $5,310 per 1 pound of gold. So we're going to go from dollars per pound, and we want to convert to this pounds per kilogram. Right? So we're going to have to convert dollars to pounds and pounds to kilograms. Right? So we have our initial mass here. We know that if we do the currency conversion first, that for every 1 US dollar, we get 0.545 British pounds, and I'm trying to make that symbol. As being a Yank, it's hard for me to do. So now we've converted from US dollars to British pounds. Right? Now we have to do the mass conversion, where we convert from the English unit of mass for pound to kilogram. So this is on the bottom. We need to have the pounds on top. We want the kilograms on the bottom. The conversion for this is 1 kilogram is equal to 2.205 pounds. So we have 2.205 pounds for 1 kilogram. Now our units of mass, pounds, cancel, and we're left with our units of British pounds per kilogram of gold. Right, so we do the math there. We come up with 6,381 pounds per kilogram of gold. Right. Again, we have to look at significant figures. Here we have only 3. Both of our conversions, these two conversions, because they are conversions, we're going to assume they have an infinite number of significant figures. So our answer should have, again, 3 significant digits. So we're going to round this to 6,380 British pounds per kilogram of gold. Let's look at one more. So the speed needed to escape the pearl of Earth's gravity is 11.3 kilograms per second. What is this speed in miles per hour? So let's think about how we have to convert from kilometers, excuse me, to miles. That's the distance conversion we want to do. And we also have to do a time conversion from seconds to hours. So to go from kilometers to miles, I know a conversion that that 1 centimeter is equal to 2.54. 2.54 centimeters is equal to 1 inch. So if we go from the metric unit of centimeters, we can go to the English unit of inches in that case. So which means that we're going to do kilometers to meters, meters to centimeters. Now the conversion centimeters to inches, inches to feet, and feet to a mile. That's one way you can do it. To go from seconds to hours, we can go from seconds to minutes, and then minutes to hours. That's only a two-step conversion. Right, so let's look at these conversions then. So 1 kilometer is equal to the prefix 1 times 10 to the third meters. We already have the centimeters to an inch. 1 meter is equal to 1 times 10 to the minus 2. 1 centimeter is equal to 1 times 10 to the minus 2 meters. Again, keep the prefix here, prefix there. Inches to feet. There's 12 inches in 1 foot. And there's 5,280 feet in 1 mile. For this bottom one, we know that there is 60 seconds in 1 minute, and 60 minutes is equal to 1 hour. So all of our conversions are now here. So now we just have to actually sit down and do that conversion there. So we're going to start here with the value that we have, this 11.3 kilometers per second. We will convert the kilometers first. So from over here, 1 kilometer is equal to 1 times 10 to the third meters. Kilometers cancel out, we're left with meters. We don't want meters, so we have to go to centimeters. 1 times 10 to the negative 2 meters is 1 centimeter. That cancels out meters. We don't want centimeters, we want miles, so we have to keep going. There's 2.54 centimeters is 1 inch. Not there yet. Excuse me. There are 12 inches in 1 foot. 5,280 feet in 1 mile. So that is the conversion from kilometers to meters. So now we do this, we're going to be left with miles per second. So we have to convert then from, ran out of room here, 60 seconds, because it's on the bottom, is 1 minute, and there's 60 minutes in 1 hour. Right? So now if we follow this conversion across, we see that the units that we're left with, there's miles per hour. Right? So if we do that math, we end up with a value of 2.5277 times 10 to the fourth miles per hour. Right? Look at the significant figures up here. We have 3 to start with. That means we have to put this equal to 3. So this is going to be approximated as 2.53 times 10 to the fourth miles per hour. Right? That's a longer way to do it based on the fact that I remember this conversion, 2.54 centimeters in 1 inch. We can also look up the fact that 1 kilometer is equal to 0.62 miles. Right? So instead of doing all of these conversions, we only have to do a single step from kilometers to miles. Right? And if we multiply this 60 by 60, we'll see that there's 3,600 seconds is equal to 1 hour. So again, we've done all of these steps here based on the fact that we knew this one conversion. Here we did 2 steps based on these 2 conversions. Right? We can combine those if we wish. If we do that, we see if we start again with this 11.3 kilometers per second. Now use these 2 conversions. One kilometer is 0.62 miles. And there's 3,600 seconds in 1 hour. Right? Again, we end up with the same units, miles per hour. And if we do that, we see that we get 2.522 times 10 to the fourth miles per hour. Again, if we rounded this to the 3 significant digits, we would get 2.52 times 10 to the fourth miles per hour, which is essentially the same value. Right? They're off by this digit here, but that is a simple rounding error because this really only had 2. If we would have carried this out additional digits, those would have been the same. Right? So we can see we do this dimensional analysis the same way. If we can get our units to work out, regardless of the path we take to be the units we want, we should get the correct answer within some small rounding error in the number of significant digits.